My name is Ole Madsen. I'm a professor here at Aalborg University. I work here at the AU Smart Lab, where I do research in robotics and in how robots are going to be used in the factories of the future. The lab is a lab where we investigate robots. So it's a multidisciplinary lab where we are focused on advanced robotics with a special emphasis on manufacturing robots. We created the lab because we saw there was a big need for robots in industry. The industry is challenged by small batch sizes, by constantly introducing new products and so on. So there was a need for new robotic systems for manufacturing. We also saw a need for multidisciplinary research, and we found that having a physical lab, a place where we could meet, where researchers from various departments could meet and do research, was very useful for the research that we were doing. We have 4 focus areas. One of them is on industrial processes. So here we do research in particular on welding and on laser installation. Secondly, we are working with exoskeletons, or doing research on exoskeletons. The research here is aimed at giving people with limited mobility the option to walk or use the upper body for various tasks. Then we do research on AI, on self-learning and self-adaptive systems. A growing area where a lot of new technologies are coming out that we really can benefit for in the robotic world. One of the projects we have there is the Little Helper project, which is a project on a mobile robot which can help you doing a simple task in your manufacturing environment. And finally, we do research on robots in larger production systems. Here we have a special focus on the role that robots will play in Industry 4.0, that is the future of manufacturing. Most of the research we're doing here is done in collaboration with companies. They come with applications and we use them as specification for our research. We also have partners who are system integrators and who are building technologies, so people who are building robots. And finally, we have a number of universities around the world where we collaborate. In the next couple of years, we want to investigate the possibility to build a swarm factory. That is a factory where the manufacturing equipment, including robots, are very, very simple, small machines that individually can do very simple tasks. But when we combine them, then intelligence will emerge, and we expect that we can design much more advanced and flexible systems than we have today.
Hello everyone, I'm Dimitris Chrysostomou, and in this segment I'm going to tell you more about our research in autonomous industrial mobile manipulators. As you may know, most industrial robots are fast, reliable and safe to use when they are behind protective fences. However, their mobility and flexibility is limited, as they have to be stationary, bolted to the ground and programmed for one task at a time. Almost a decade ago, here in the Robotics and Automation group of AAU, we developed a robot assistant which can coexist with users for safe and easy interaction. We call it Little Helper, our flagship research platform which we use to bring flexible solutions, easy to program and integrate into a variety of industrial tasks and scenarios. In collaboration with many industrial partners, we have developed different versions of our Little Helper research platform. It is a modular platform that consists of mobile or movable bases, while it can support 1 or 2 robotic manipulators. It adapts accordingly depending on the level of interaction we want to accomplish with our users. Sometimes we have to tackle tasks where we need to work away from users, executing everyday procedures such as delivery scenarios inside our smart production facility, where mobility, precise calibration, localization and mapping are very important. We also want to facilitate users who work in sensitive environments, where human presence should be limited. In these cases, we employ virtual reality and augmented reality techniques, which can provide a unique perspective of the working environment to the users, while they operate Little Helper from another room. Assembly of industrial parts is another area where we use Little Helper extensively. It is a very demanding task where advanced robot functionalities such as force feedback and station calibration are critical. In these cases, accurate object detection, recognition and grasping are very important as well. On top of everything, Little Helper is developed to enable non-expert users to use a robot in everyday industrial tasks. For that reason, it runs a skill-based programming interface in the background which has been designed to facilitate easy and fast instruction of collaborative robots by inexperienced users, while it supports quick integration of existing off-the-shelf components in terms of hardware and software packages. Naturally, when we collaborate in close space with users, safety is a top priority in our research. Therefore, we have equipped LidiHelper with user detection methods based on image processing and artificial laser walls. There, LidiHelper can detect the user and adapt the speed of the robot arm, and it can communicate its current operating status with color-coded visual feedback. Finally, LidiHelper is also the platform we use as basis for our future robotics research. Towards our vision for a more sustainable society, many of our current projects focus on assistive human-robot collaboration tasks for automated disassembly processes of electronics and industrial components. This way, we promote circular economy initiatives and reduce the environmental footprint of manufacturing industry. Stay with us, as Kasper now will present our future research direction on swarm production, and later Simon will dive into our AI research in industrial robotics and manufacturing.
Thank you. I'm Kasper Skov, and my primary research is within solutions for smart factories. Let me present to you our research on swarm production, which is a new upcoming research area where we combine the domain of swarm robotics with industrial manufacturing to achieve high flexibility on the shop floor. Here in our AAU 5G Smart Lab, we have established a smart factory environment, including a Festo CP factory production line, our mini robots and little helpers, operator assistance tools, and not least a suite of digital solutions interconnecting these assets. In terms of flexibility, even this Industry 4.0 production is inherently constrained by the use of conveyors as they route products along fixed paths, limiting us to a sequential flow. With offset in this constraint, we are motivated by the vision of having products transported using cheap, small, mobile robots to create the production paradigm we call swarm production. Using mobile robots not only gives us large routing flexibility, but also makes the system more robust against failures, allows easy scaling of capacity, introduction of new processes without system downtime, and allows individual order flows and priorities. We imagine the swarm will be composed on a variety of different robots with different capabilities, ranging from small part-carrying robots to little helper-sized processing robots. Currently, we are carrying out early design sprints, experimenting with the layout and composition of both part-carrying robots and processing robots. To decrease the cost of the mobile robots, our architecture centralized the navigation and online route planning of each robot on a central edge cloud. Thus, fast, low latency and robust wireless communication is required between the robots and this edge cloud. For this, we have built up an infrastructure with both private and public 5G networks, Wi-Fi 6, and both an ultra-wideband and an ultrasonic positioning system. An infrastructure that allows reliable and low latency communication, even when using a swarm of devices. Finally, retaining production efficiency while exploiting this flexibility offered by swarm robotics calls for very frequent task plan updates. Together with our colleagues from computer science, we are working on distributed, near-optimal task planning and scheduling strategies using the AI technique called Q-learning. Some of these strategies we are currently testing out in large simulation environments, including hundreds of robots and a highly dynamic order flow. And now over to my colleague Simon, who's going to present much more in depth about our AI research.
Hi, my name is Simon Bøe. In our next part of research, AI for industrial robotics and manufacturing, we are tackling the AI gap between research and industry, where we focus on adaptive and self-learning robots and automation systems. AI is redefining the landscape of intelligent robotics and automation in manufacturing industries. We help manufacturing companies navigate and demystify the hype around AI and put it into practice. We do this through student projects, research projects, and strategic collaborations with the companies.
Let's have a look at some of our projects. Deep reinforcement learning is one of the pinnacles of AI today. In one of our projects, we work with robot grasping. How can we enable a robot to, on its own, learn how to grasp objects without knowing anything beforehand? The robot acts as an autonomous agent where it learns how to act optimally and carry out the task without any supervision from a human. Through the interaction with the object and the environment, it receives rewards, and over time it learns how to act in an optimal way. We also use this technique for mobile robot behavior and navigation. So how can mobile robots learn how to navigate a human environment in an optimal and safe way? Human-robot interaction is always critical in many robot applications. The natural interaction between the human and the robot we enable through natural language processing and acoustic analysis. We design and develop voice assistants so the human worker can naturally interact and talk to the robot. Through various commands, the robot learns how to carry out tasks that are given by the human worker. Acoustic analysis can also be used for other industrial processes, for instance robot welding. By recording the acoustic signals and time series data from the welding process, we can analyze and assess the quality. We also rely on computer vision in many of our robot applications. So a robot system or industrial task without eyes makes it very difficult to solve the task. In one of our projects, we detect defects on offshore platforms. This is usually a very tedious and dangerous task, which requires a lot of manpower, and in the end it becomes very costly because we have to send humans to the offshore platforms. By designing an automated system, we can detect certain defects and automate the maintenance process needed for these kind of industries. Finally, we want to enable artificial intelligence for the small and medium-sized enterprises. These days we see that AI is primarily for the universities and larger companies who have the budgets and skills to actually carry out a deep learning project. Through one of our projects, we investigate how we can enable advanced technologies for the smaller companies so they can also harvest the benefits of artificial intelligence. In this case, we need to wrap the methodologies and models in an easy and intuitive platform which can enable the shop floor worker to actually train the network without knowing anything about deep learning. In this case, we want to be able to feed many different kinds of data inputs, which can be time series data, acoustic data, images, videos, and so on. So AI is a natural enabler for improving the manufacturing industry of the future. Our vision is to continue close collaboration with the industry and enable these technologies and make them accessible for both big and small companies.